Right, now we get into some of the most interesting bits. So invocation of the Poker Virtual Machine, PVM. Right, we're going to define A. A isn't really a pure function. It has, well, okay, it's not really a function at all, because it requires it assumes some omnipresence of a time slot, HT, and also some prior state components. If I were doing this as a proper mathematician, I would be passing these into A, but that just makes it less readable, so I'm not going to do that. You can just assume that these things mean what you expect them to mean. But it also takes as specific arguments the service index, S, which is drawn from this set, capital bold S, the set of all service indices that we are moving forward, that we are progressing. And then from this, it can derive the wrangled results, MS. I mean, M is also a bit of a dodgy function because it uses W, this big fat bold W, which, you know, technically it doesn't have access to. It's not one of the arguments, but you know, we know what it means, so it's fine. Okay, so yes, from this it can derive the wrangled results MS, and then the gas limit GS, another function that again we actually made some assumptions on the knowledge of delta, and it yields value. Oh dear, delta shouldn't be bold. And yields values for delta, dagger, S, and staging assignments into some other variables. So basically, accumulating the PVM, it's this accumulation that allows us to set iota, which is the next validator set, the next keys of the next validator set, and phi, which is the pools, right? The authorization pool, queues, sorry. The thing that feeds into alpha, the authorization pools. Together with a series of lookup solicitations and forgets, basically the outcome of our lookup host functions, a series of deferred transfers, the outcome of our transfer host functions, and yes, and this big bold C, which is essentially our beefy inputs, beefy commitment hashes. Every accumulate is allowed to output a hash for beefy. And this makes its way into a Merkle tree, whose root makes its way into that Merkle mountain range that we eventually feed into Ethereum or whatever. Good. Now, let's start by denoting a type for the set of deferred transfers. So T, Blackboard T, is a deferred transfer. A deferred transfer is a service index for the source, a service index for the destination, an amount, balance, a memo to explain why we're doing this, and some gas, which is the amount of gas, this again should really be an N, the amount of gas that we want to provide to that destination service to process this transfer. This amount of gas gets, our own gas counter gets reduced by this amount of gas. So we kind of pay them with our own gas. But we decide ahead of time how much gas we want to reduce. It's a little bit like a message call in Ethereum, right? The main difference is here it's not synchronous. We maybe make it synchronous in the future, but at this point, everything is quite a lot simpler, at least in the grey paper, if it's asynchronous. So, and the use cases that we need to manage can all be managed asynchronously. So I'm kind of like a little bit loath to changing it. But this is something that after we've actually implemented it and we start playing around with it, if we find that certain applications are very hard to do with asynchronous transfers, we may switch to a synchronous transfer model. Right. I mean, but otherwise, it's pretty obvious, these fields, I would say. Just, right, almost there, almost there. Got this one page, and then I think we're done. So we then define capital A. This is the biggie. This is the mapping from the index of a service. So for each service that is accumulated into these components. So the way that I'm expressing this here is I'm not trying to bring in sort of state and then mutate it in place as the virtual machine operates, and probably as implementers, nor should you. Rather, what I'm doing is saying, these are all the state changes that the virtual machine needs to collect. And then after the execution, they can be applied to the state. And the way that it's designed, there's only one or two instances where they're synchronous with other services execution, which means you can execute different services at the same time, right? This is ready for parallelization. Now, it's probably not going to be particularly useful to parallelize service accumulation at this stage, because probably there's going to be one massive service and everything else will be really small, and executing them at the same time isn't going to save much. But in the future, especially if we start dedicating multiple cores into accumulation, this could help a lot. All right, so service index is the input, and we're going to see how, no, actually we don't need to see anything. Service index is the input. The output is this rather fat tuple with no less than 7 items. S, V, T, R, C, N, and P. Let's go through these. C, sort of, did I actually describe any of this? I don't think I did I? Oh dear. Right, so I think 162, yes, this is all described in the appendix. But let's go through and see if we can work out what it is anyway. So, T is easy. T is the sequence of deferred transfers, so it's basically all the transfer host functions that have been called in a sequence. Yeah. So all of the source is all going to be the same. The source is going to be the same as S, because that's the service that's executing. The destinations will be different, but probably. They'll be for each transfer. The amounts, memos, and gas amounts will accordingly be different. So T, the sequence of transfers. S here, bold S, which is A, an A, possibly. I've got a feeling that this might be to do with beefy, because I can't see anything else that is beefy. But I'm not gonna, I'll have to check the appendix first. What else do we have? Right, C is the thing that we are going to replace our pools with. And if we go down here, we should see this. Okay, so I'm not gonna go into describing these quite yet. I think these will become very obvious once we go into the next equations. Right, first thing that we do is we look at the accumulation tree root for the Beefy protocol. So go through all services who, when we accumulate the service, their R, this guy, is not nothing. Okay, so that should probably be a question mark. So R is the result of accumulation, which is a hash that feeds into Beefy. Here we've said the R shouldn't be nothing, which basically means this hash, this is actually a hash or nothing. That probably is already corrected in the appendix, but anyway. So we're going to take all of the R's and we're going to combine it with the service index, make a pair, and call this set of pairs big, bold C. Big, bold C is what makes the Beefy Merkle tree, Merkle root, and that is what gets fed into the Merkle mountain range. Okay. For what it's worth, in Polkadot 1, this was always fixed at as some particular value, I think like the parachains roots. But here, we're allowing a service to just decide what data it wants to place in this Beefy Merkle mountain range under its service ID. So different services might use the Beefy facility in different ways. But all they can do is place a commitment. They can't like store data in here or anything. But they might, how they define what their commitment is up to them. Right, that takes care of R. Yeah. I'll do that. Okay, what's next? Chai. So, Chai prime is our accumulated service of Chai M and the P thing for that. So if we look at P, where is it? Here. So P is a tuple of 3 service indices, exactly the same format as the state Chai, state item Chai. So we're just replacing it. And basically it's up to this service, Chai M, to yield a P from accumulation to replace Chai. Yeah? This service decides what Chai is. That's its right, that's its privilege. And if someday it decides that Chai M isn't itself, then it will pass the baton effectively to some other service to decide what Chai is. Next, we have Phi prime. Phi is going to become the accumulation of Chai A, the C item of that. C is the core assignments, as defined by a sequence of Q hashes, themselves sequenced C in a sequence C large. Yeah. So for every core, a Q. For every core, a queue of Q hashes. Yeah. That's the authorizations queue. And again, we're using Chai to do this, not Chai M, but Chai A. A is the service index that gets to state what these authorization queues are. Iota prime is basically the same thing, but it's Chai V, and it's the V item from accumulation, which is here. It's the keys for validators. A sequence of V validator keys. This should actually be well done if you noticed it. Oh dear, might need some power. Should actually be that. Sequence of keys, sequence is V entries long. Okay, so that's the privileged transitions. Service account transitions. this is the meaty bit. This is where we're going to move services along in their state. So we're going to integrate all changes to the service accounts into state from our accumulation results. So our accumulation results, A. So we're going to go through all services. All of the keys in the N component of the accumulation result intersected with all the keys of the delta, this first, this only intermediate value of delta is the empty set. Okay, so yes, okay, right. So N, this N field is a dictionary of new services. Nice one, thanks. This N output is a dictionary of new services. So services that have been created by virtue of the PVM. Now, as I mentioned before, all of these PVMs are expected to be, or at least in this model, they can all execute simultaneously. They don't interfere with each other. Now, we have a slight issue. If a new service is created, what index do we give that service? If we're dealing with like 32-byte identifiers, it's less of an issue because we basically just hash our current service hash with an index, and it's basically fine. It doesn't really work for 32-bit service identifiers. We're not sort of guaranteed of getting something that is unique. We do actually do that anyway, but on the very, very, very unlikely chance that's still actually practically possible that two services both create a new service with the same index, we say that the block is invalid. It's like a 1 in a million chance of happening, but you know, how big is Polkadot now? Like a few million blocks, so it could actually happen. It could actually happen. So we have to, this is what this first line says. It says, look, if it ever does happen, then, I mean, actually what this first one says is, if we ever manage to create a new service whose index is already a service index, then like something really bad is happening. This is already protected against, so this actually won't happen. This won't happen by virtue of the PVM create service host function in the appendix. This one is saying, well, look, if you look at all of the services that are both created, that are created by two different services, and therefore two services that could each have created a service with the same ID accidentally, then make sure that that didn't happen. Make sure that there isn't a service index collision. Right? That's what it boils down to. Now this we cannot protect against definitively because, as I say, our model is that these services execute all without reference to each other. It's a lot easier to define, and it turns out it's probably quite a lot easier to optimize. Right, next, we first define delta double dagger. All right, so we do have an intermediate value of delta, or a second intermediate value of delta. And this is the this intermediate value of delta is after we've done the main part of state transitioning, but before we've done all of the transfers. If you remember, transfers are asynchronous. They don't happen as part of the main accumulation. They happen at a stage later. So before the transfers have been credited and handled. How does this look? Well, firstly, the keys of this second intermediate state of delta are the keys from the first intermediate state of delta plus all of the newly created service indices, minus all of the services that have basically self-terminated. That's what this S is. This, if it's true, if it's something, no, if it's something, it's fine. If it's nothing, then it's then it means it's terminated, and we are removing that service index from this set. So basically, we're going to remove the keys of the services that self-terminated. Secondly, the keys that are left. A service S is defined as, well, we define our otherwise as being remaining the same, right? So now we only have to look at to see how would it change. Well, it might change if S is being accumulated, if it's in the services that are being accumulated. In this case, it is accumulation of service, so we're accumulating the service, and then we've got this S field. Let's have a look, see what that is. Of course, it's the account. Blackboard A is the service account type, and so when we give a service over to the PVM to be accumulated, we hand it the service account so that it can change things like the balance and whatnot, the code potentially if there's an upgrade going on, lookup stuff, and all the rest of it. Okay, so that's pretty straightforward. Now, if there doesn't exist some T such that T is a service, so if there is no service T whereby S is a member of the keys of that service's N, new account creation. So basically, if S is was created as part of T being executed, then we want to introduce it into our state, into our account state. And in that case, it is the accumulation of T, new service, S. All right? So this new service, N, is a dictionary of service indices to accounts. So it's basically the new services that we've created that we want to merge into Delta. After the dust has settled, we want to merge these things into Delta. That is this lowercase bold n. And we're looking for this, basically the service S is a member of some service that was accumulated T's N subscript. I think this should actually be just, oh, no, that's right, yes, sorry. E, if you're not familiar with that notation, E exclamation mark is a unique. There exists a unique service T. I could have not put the exclamation mark in, but I think it shows that I'm expecting it to be a unique service. If it's not a unique service, if multiple services have managed to create this same service S, it would already have failed 165. Yeah, but I put it in just so it's very, very obvious. Only one service should be, if a service is being created, it should only be created by one sort of parent service. If two parent services collide, then the block is invalid. All right. Now, finally, we're going to denote R, this function R, as being the transfers that one service did. This is really easy. We're going to take all the services that accumulated, take their accumulation transfers, and look for all of the transfers that had our service D as their destination. And then pull them all together in order of services and transfers out, and then stick that in a sequence T. Okay? So we do this after all of the services have finished their accumulation, and we have a PVM. PVM is all finished, and now we have a sequence of transfers for each service. Finally, this magic little line here, 168, tells us our posterior delta, given our transfers. I mean, it's R, so it's actually sort of the receiving transfers. It's on the receiving side. We're transfers out, but actually we're collecting them according to the receiver. Now, it so happens that this big capital phi t is defined so that it results in no change, results in the original delta double dagger, if R happens to be empty. So basically, if you're not given any transfers, this is a no-op. So in the implementation, you can just basically say, if there are no transfers to a service, ignore it. Here, it's just easier to write it as uniform, as a uniform thing. Okay, so this big phi t, we're passing it in the delta double prime, so the intermediate state of all the accounts, the received transfers for an account A and account index A. And we're doing it for all so we're taking our delta, yeah, of course, right. So we're taking our mapping, our dictionary, which is our service dictionary that maps service indices to accounts. So we're taking every service index, every account, and we are putting it into this set here. But instead of it being the actual account, we're changing that through, we're transforming it through this big phi underscore t function to give us what the account looks like after it's received its transfers. Yeah. So basically mapping all of these services, but we're mapping it through this process transfers function, that is effectively. Now these big phis, big phi t, big phi a, these are PVM, they're at quite a high level, but PVM execution functions. So big phi t is the PVM process transfers function, and big phi a is the PVM do accumulation function. They're fully defined in the appendix. I'm not going to go into it here, but they're pretty, I mean, it's straightforward. It's obviously not super simple, but there's no big dragons there or anything.